jump right in to getting scatter plots done. Right. So what we have here is essentially a scatter plot. And this particular one is to do with an animal and the animals, and they measured them at 1, 2, 3, 4, 5 months, and they got their weight. And what you have here is a pretty straightforward scatter plot. Would you agree it's positive, moderately strong, no sign of any outliers? And that's kind of what we've been doing. And so let's introduce you to some more terms. The horizontal axis, the x-axis, is the age, and the vertical axis here is the weight. The x-axis, this variable age, is called the explanatory variable, and the other one is called the response. So if you hear them talking about the explanatory variable, they're talking in this case about the age, the x-axis, and if you hear things about the response variable, it's this. And those terms very often come from the medical field. I suspect that's where they came from anyway. So the explanatory variable might be something along, I gave them 1 unit of the drug, 2 units of the drug, 3, 4, 5 units of the drug. And the response is, well, what happened when I did that? Well, their blood pressure went up this amount, they went up that amount, and so on. And they would have a relationship between the two variables. But one of them kind of explains what's going on, and the other one is the response. What happens when you do this? What happens to that? Now, when you've got data, and now we're only going to focus on one kind of data, and that is linear data. So the curvilinear stuff is kind of left the building there. When you get a nice scatter plot that's pretty good like this, wouldn't you say that it was linear, right? So there's a straight line that goes through it. That line is called a regression line. It has other names, but it's called a regression line. And the regression line is the best fitting straight line through the data. Now, do you notice that that straight line does not pass through all the points? But there's no way in the world one straight line could. But have you got the idea that the best fitting straight line is the one that it passes through the most, or at least is close to them? Now, what you might not realize is that that line is unique. In other words, there's one line that does a better job than any of the other lines that you could do. So if I did this one, it's a little bit high, a little bit low, this is miles off, this is a little bit different, this is a little bit different. There's one line, this regression line, that's the best fitting line that passes through the data. And it can be calculated, but not by hand. That's too cumbersome. You get the computer to do it. And when the computer gives you the equation of this line, it will look something like this. Y equals, just like a usual line, 3x plus 5. And you know from your algebra classes, isn't that the general equation of every line, right? Y equals so many x plus or minus a number, right? Now, that is not the way that we like these equations to be written down, because age is x and y is weight. So we would do something like this. You put a funny little hat on, and I'll explain what that is in a minute. And you go 3 times age plus 5. So do you see the x is replaced by age and the y is replaced by this weight with a funny little hat on it? And that's because this is the predicted weight. So that funny little hat on the top is predicted weight, rather than saying, in English, we put a little hat on it. So the predicted weight is 3 times the age of the animal plus 5. Does that seem reasonable? So if you took a typical animal from this group and you found one and it was 4 months old, whatever way you figured it out, it was 4 months old. then its predicted weight, if it was 4 months old, should be 3 times its age plus 5, which should be about 17 ounces because it's a tiny little creature. And so what you've got here is a formula that allows you to predict what the height of this animal would be at various ages. The typical, whatever this is, the typical, try to think small, the typical Scottish mouse at 4 months old will weigh 17 ounces. That's a big honking mouse, so I guess it's a Scottish rat then, right? Now, can you put in other numbers there and get other predictions? Now, in real life, if you found a Scottish rat that was 4 months old, because you were there when it's got born and you've kept it in a cage, and it was 4 months old, you would predict it to weigh 17 ounces. But in real life, don't you get a bit of variation, right? Some rats are a little bit bigger when they're 4 months old. Some didn't get as much food, they're a little bit less. So you've got a predicted weight, and then for a single animal, you'll have its true weight. Now, its true weight might be 17 ounces, but let's just say for argument's sake that this particular rat weighed 18.5 ounces. So what you're saying here is that this rat is a little bit heavier than the normal 4-month-old rat. And we have a term for the difference between what we predicted it would be and what the true value is. And the term is called the residual. And you are asked to find this in some questions. So the residual is the difference between the true weight, take away the predicted weight. So in this particular example, the true weight was 18.5, predicted weight was 7, so the residual is 1.5 ounces. You can think of residual as the error, is it not, how much we were out in our prediction? If you have very good data, right, a nice linear, really strong, these residuals tend to be very small numbers, right? You tend to either be bang on or maybe, half an ounce out, right? If this data is linear, but it's like moderate, the residuals very often will be bigger, right? You'll be out more often than you're not, and you'll probably be out by a couple of ounces. And if this data is weak, then this residual could be anywhere. You could be miles off sometimes. Any questions about kind of this situation, what we've described? Are we good? Right. So what I'm going to show you is first, how do you do scatter plots using salt and getting these equations, right? The regression line equation. How do we get salt to calculate that? Because I said this is the best line and it's unique, right? There's only one answer. So all of what I'm doing, you can't really do by hand, right? So if you try to do it by hand, trust me, if you saw what the calculation was, you'd probably leave the class, right? If you say, you think I'm going to do that 8.5, right? I wouldn't even do it by hand. So let's have a look at one. Right, I'm assuming you can see this big table, right? There's a lot of data here, not all of it is going to get used. This is mostly for informational purposes. Now, here is Miami. It's a latitude of 26. So if you're wondering what the latitude is, can you imagine that the equator is a big circle around the middle of the Earth? And every degree you go up is called a latitude, right? So for instance, if you did 90 degrees latitude, you'd be in the North Pole, roughly. Now, Florida has an average August temperature of 83, Miami at least, and a January temperature is 67, which is why when I retire, I may end up in Florida because I don't like the heat. So they're getting hopefully good weather right now. Now, if you go through each of these, you've got a latitude. Let's see, what's near us? There must be one of them near us, isn't there? Let's see if I can find one.
Portland.
Portland, yeah, Portland. We're a little bit further north than Portland, right? So in Portland, 46, right? That's like that. We're probably a couple of degrees more. So we're probably about a latitude of 48, 49, I'm guessing. And for that, the winter temperature, the summer temperature is 69 and the winter average is 40. So we would like to make a scatter plot of this data. And the one that they want us to do is August temperature against latitude. Now notice the Y value is the August temperature and the X value is latitude. So the X sky, we would call that the explanatory variable. Your latitude affects the average August temperature, right? Would you agree the further north you go, the colder it gets, right? That kind of connection. So you hit the salt button. And the good news is it already knows. Can you see? I know it's a bit messy, but can you see the latitude and all the temperatures here? So we got that. And you go and you hit the regression line. See this guy right here? Hit that one. And explanatory variable was latitude and the response variable was August. Do you see how I chose those two according to what they wanted? And what you're looking at here is the scatter plot. Would you agree it's linear? Agree on that? Negative? Right, sloping downwards, negative. You might think that these dots are very spread out. That's really not the case. Do you notice that this axis here starts at 64 and finishes at 90? If it started at 0 and finished at 90, wouldn't all those dots squish together and it would be a much better looking straight line? So be very careful when politicians show you diagrams and the right-hand side scale doesn't start at 0. Because what they're trying to do here is make something exaggerate what's happening. So if something is going down and they use that trick on it, it will look like it's shooting down like, oh God, we're all going to die, right? So watch out for that cheat. Now, I would like to see that perfect fitting straight line. So if I hit that guy, can you see the line? That is the regression line. That's pretty cool. Now, I wish they did this better, but we're going to have to live with it. In this mess here, the formula is hidden. The predicted August temperature is, now do you see how it says latitude X and then it has a number negative 1.006? Well, you switch them around and call that negative 1.0062X plus that number. You see how that's just not a good way of doing it, but I don't have any control over it. So I would actually, wouldn't you just probably call that negative 1x, because the number's almost negative 1 anyway. So you'd call it negative x, which I'm writing down right now. We'll see where that takes us. So the predicted August temperature is going to be negative 1x plus 113.6. And we will now leave this guy and look at some of the things that we can do with this type of diagram that we've got. So remember that nice straight line that looked up? No, it's pointing down the way. Negative 1, this fella. Let's suppose there is some city in America called Robertson Town. No, let's call it Robertsonville, right? God, America's big enough. There probably is a town called Robertsonville if you go hunting for it, right? And in this town, the latitude is 31 degrees, right? And we would like to know what is the predicted August temperature this coming year for Robertsonville. Well, it will be negative X plus 113.6. So go to my calculator and just go negative 31, add 113.6. Helps when it's on. Negative 1, negative that guy, plus 113.6. And the answer we get is 82.6 degrees. Isn't that quite a nice summer average? Average is 82. Right. You didn't know this, but there's another town in America called Gilberttown. Did you know that? There was one called after you, Ian? You know I'm making this up, right? And you are in Alaska. And your latitude is 59 degrees. Do you think the average August temperature in Gilberttown is going to be warmer than 82 or colder than 82?
Colder.
It's going to be colder, right? And in this particular case, the predicted August would be negative 59 add 113.6. And negative 59 add 113.6. And we get 54.6 degrees. Right, nobody wants to go there.
So the equation is different for every graph.
Yeah, for every scatter plot, you have a different. I'm using the same equation. I'm using the predicted August is negative X plus 113.6. I'm using that equation in every one of these stories. But do you see the X changes in each story?
Right, but if you had like a different graph, like the one we did about animals and their weight.
Yeah, that would be a totally different equation. That might be, actually, it's 3 times the age plus 5, that particular one. If it points up the way, won't it be a positive number of X's plus or minus something? If it points down the way, it's a negative number of X's plus or minus something. That's the general shape that they take. Let's do a residual on this. Let's suppose that that's the average August temperature in Gilberttown. And August came and went. And it didn't actually work out that it was exactly that, right? The real answer, at least this year, was 53 degrees, right? So it's a little bit colder than it typically should have been. And we can now calculate the residual. It's the real answer. Take away the predicted one. And the real answer was 53. And the predicted answer was that. So it's negative 1.6 degrees. Can you see sometimes the residual can be negative as well as positive? Right. Sometimes the real answer is bigger than what you predicted, in which case you get a positive residual. Sometimes it's a little bit less, in which case you get a negative residual. And sometimes the real answer is bang on. It's the same number. So when it matches exactly, won't the residual be 0? Right, you got what you thought you were getting and it did happen. Any questions? Are we good? Okay. See if I can see another one. Okay, here we go. Let's look at another set of data and do some analysis on it. This is question 7, at least my question 7. The data in the following table shows the square footage and the asking price of 9 homes in Orange County, California. Yikes. So if you were trying to buy this particular house, which is about 2,300 square feet, it's going to cost you 443,000. If you wanted to buy this house down here, the answer you get is over 1.5 million, right? It's almost 1.6 million. I like watching TV programs about houses. Isn't California ridiculously expensive? I'm sure there's cheap places, but in general, ridiculously expensive. So 1.5 million for a house is not that unreasonable in a place like that. I think it'd be pretty rare here. Would you agree? It'd be hard to find a $1.5 million house in Bremerton. There might be some, but they're pretty rare if they are. So we are going to take this data, square footage and asking price. The guy that's in the first column, in this case square footage, is going to be our X, the explanatory variable, and this is going to be the response variable. So I'll hit that. Okay, looks like the data is transferred. I'll hit regression line. The explanatory variable is the square footage. The response variable is the asking price. Not a lot of data here, would you agree? You got to watch that scale. It makes things a little bit distorted. But I'm going to put in a regression line. And it's positive. You see, it's a little bit easier when you see the line. In this case, that makes sense. Would you agree that typically a bigger house should cost you more, right? More square footage? Now, there's the scary formula. The asking price of the house, I'll write that down, is, so I'll call it the predicted price. It's that guy, 0.2816. The square footage, I'm just going to call that the area of the house, plus 52.1507. So everything that we want to know is here, right? You get it from that thing. And now we're going to go and return back to our thing and ask some more questions based on that. So they could, for instance, say, what does the scatter plot look like, which they did. But I'm going to ask some other questions. That's a very small sample size. I would have done this with a couple of hundred houses. But suppose someone goes to the real estate agent and they say to them, I'd like to sell my house, and it's in the same area as these houses. Wouldn't you kind of like to know how much your house is probably going to sell for, at least how much you should ask for it? And so somebody comes up and says, I have a 2,000 square foot house. What should I sell it for? Well, now that you've got this formula, can't you do a predicted estimate of it? So you would say, well, the predicted price, this is what you would say if you were the real estate agent, is 0.2816 times the area in square foot, 2,000, add 52.1507, and I'll do that calculation, 0.2816 times 2,000, add 52.1507, and the answer comes out, and I'm just going to round it off, as 615. But remember, that's how many thousands. So you would say to the person, you should be able to get 615,000 for your house. That's the typical going rate for a 2,000 square house. And couldn't you do a 1,500 square foot house and a 5,000 square foot house and anything else that you were interested in? And can you see then, if you had wondered before, how do the real estate agents decide what your house is worth, right? So if you're selling your house and you're saying, well, how do they come up with this number? You'll hear them say comparables. What that basically means is they try and find houses near to where you are that are roughly the same size, and they use those numbers. Basically, they don't know they're doing it because they just have a piece of software, but they're taking those numbers, doing a scatter plot, and then the best straight line through it, and that guy pops out at the end, and that's the guy that you use. Well, let's suppose that there was two houses, and both of them were 2,000 square feet. This house ended up selling for about 600,000, which is not too far away from what they predicted it would be, right? You're never going to sell it exactly at that number, hopefully close to it, maybe even more. This house was way, this house would be considered an outlier. Nothing to do with statistics, this question, but how could you get a house that's the same size as another one, but a lot cheaper? What are the kind of things that make a house sell for less?
If it needs renovations?
Yeah, if the roof is leaking and the yard's got a broken down car in it and things like that. Don't the quality of the house have a big effect? I would agree. That's a good reason. Suppose the house was perfect, and perfect's never exists, but it was just as good as the other one. So it wasn't the house quality that was causing the problem. There is another feature that tends to affect the price of a house.
Location.
Yeah. If your house is in the middle of a really crime-ridden, drug-infested area, you're not going to get the same price, are you, as if it was in a nice kind of suburban, safe area, right? Location, 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 right? Those things are what distorts this data. So when you're collecting data, try and make sure that the data is consistent in some way. So if somebody says, okay, I've got my house, it's 2,000 square foot, what do I expect? Wouldn't one of the things you do is have a quick look at, oh God, that neighborhood you're in is not great. And so you would look for comparables, houses that are roughly that size, and make your equation from that data. On the other hand, if you have a 2,000 square foot and the guy says, oh yeah, that's a very popular area, people like houses in that area, won't you take your comparables from different numbers? Because the straight line you get comes from the data that you use. So you have to be careful to use good data to get good predictions. Make sense? So that's the practical thing that you should do if you're ever interested in becoming a real estate agent, for instance. But this works equally with almost anything. Scientific connections can also be done that way. So far, so good? I think it's good. Right. I'm going to cut right into the equation then. Let's suppose that we have a formula for predicting the height of children. And the height of the children ends up being 5 times their age plus 19. Let's just say that's the formula. Right, these are for Scottish children. And this data was collected from babies, so it's year to 10-year-old. Right. Now, I've made this data up, so take it with a pinch of salt. You don't know, because it's not true, that Scottish people are actually quite tall for their age. So if I had a 5-year-old, the predicted height of that child would be 5 times 5 plus 19, which is 25, 35, would be 44 inches. Okay, a little bit more than 3.5 years, right? Are we okay with, you could use that to predict a typical 6-year-old kid, typical 9-year-old kid, a typical 10-year-old kid. And that is what we use these for. Now I'm going to do something stupid. I'm going to use this formula to predict the height of a 30-year-old person. So the predicted height would be 5 times their age plus 19. And I get the answer 169 inches. Would you agree that is not even vaguely realistic? And the reason that that's the case is that when you do linear regression, that's the fancy name for plotting data and drawing a straight line from it, you have to be really careful about what values you collected it for. If I did a scatter plot of heights of people, 20, 30, wouldn't the data look something like that until you got to about, what, 19, 18, 19? And then doesn't the data basically flatline? But we have made the prediction based on that set of data, right? We've been making that prediction. Do you see how unrealistic it gets the further away you go from what the real data is? Now, if the real data was linear all the time, you'd be fine, right? If people just kept on growing, every year we got bigger, right? So can you imagine a 90-year-old might be 12 feet tall by now, right? If that worked, then that's fine, right? That's totally agreeable. But don't you have to be careful if the data has not been collected for the entire range? Shouldn't you be careful about predicting anything beyond 10-year-olds? Because that's where my data came from. They even have a fancy name for this problem. It's called extrapolation. Politicians love to do extrapolation because extrapolation allows them to exaggerate trends. Give you an example. Suppose over the last 3 years, the inflation rate went up by an extra 1%. So it was 5%, and then it's 6%, and then it's 7%. We'll call that year 1, year 2, year 3. Now, if you do extrapolation, won't you be able to say, oh, in 10 years from now, it's going to be 15% inflation rate. And in 30 years from now, the inflation rate is going to be 90%. And people start getting all scared and worried. Because what you're doing here is making a false assumption. You're making the assumption that whatever it is you're measuring is going to continue the same way that it did in the past. Don't things go up and down in many situations, right? They go up and they go down. If I look at set of data, and this is time, and this is the average temperature, and you might get data that looks like this. And you will draw your nice line, and you will make the prediction that the temperature is increasing. So every year it's getting hotter. And next year it'll be hotter than it was this year, and so on and so forth, right? And then you will make the big leap to, in 20 years from now, Washington will be a desert because the average temperature will be so hot the water will evaporate. If you take a bigger look at that data, and I'm talking over thousands of years, not over 100 years, Isn't that what the temperature does in the world? Do you know we've had, at least as far as I know, do you know we've had 5 ice ages? We've had more, but there are 5 ice ages that we've managed to detect. Right. Where I come from, Scotland, do you know that that was covered in ice, glaciers, 50,000 years ago?
So is Washington, I think.
Right. And the temperatures get warmer, right? And off we go. Do you know the Sahara Desert used to be a rainforest? It used to have trees and rivers and everything. And now it's a desert. And it became a desert long before people did anything to it. So you've got to be a little bit careful about data. I don't like people who tell me things like, I'm going to die in 20 years if things don't change. Do human beings screw up the environment? Sure we do. We're really good at making a mess. But isn't the world even bigger? Do you know the world could screw us up by having a couple of volcanoes? That'll change the weather a lot more than we could ever do it. A couple of really good volcanoes, put some ash into the sun, and you'll really know what cold looks like. When Krakatoa exploded, they had, I think, 3 years of almost a mini ice age. Ranting on about this, but get out of my system. I am old enough to remember being told that we were going to actually freeze. The world's weather was changing because of us, and we were going to have an ice age. And then the guys told me, we got that wrong. We're all going to burn to death instead because the Earth's going to heat up. And then they got that one wrong. And they said they got it wrong. Well, they actually never tell you they get it wrong. They just tell you something else. And now we have got global weather change. Is it called global climate change, isn't it? I believe in global climate change. I just call it the weather. I don't trust people who can't tell me what next month's weather is going to be like and assume that they know what 100 years from now is going to be like. Anybody who's good at that prediction is doing this thing. They're doing extrapolation. And I've seen enough weird stuff in my life to know extrapolation is really dangerous. Now, could they be right? Yeah, they might. In which case I'll look really stupid, but I'll be dead for about 80 years, so I guess it won't matter. So just a warning, don't do extrapolation. It is just not a good thing to do. You might get lucky and it works, but you're just as likely to be wrong. Now, another thing that you can do with these guys, and this is even worse than extrapolation, and it even has a phrase. Causation, right, sorry, get it the right way around. Correlation is not causation. Correlation is not causation. So I want to show you a downright stupid set of data that kind of shows this. Along the bottom, we're going to do the average number of TVs that a country has. So you can have 0, you can have 1 in a household, 2, 3, and maybe there's some countries with 4. So if you took your house and you counted how many televisions do I have, right? And you averaged it out amongst all the houses in America and China and Japan and Korea. And on the vertical, I'm going to do life expectancy. So for each country, what do you typically, what's the average age that someone would live to? So it might be 50, might be 60, might be 70, 80, some countries it's well into the 80s. You will see data that looks like this. Each one of these dots would represent a country. It's remarkably linear and positive. And the regression line is that. We use the word correlation just to mean how good is that data? Would you agree that there's a strong correlation between the average number of TVs that a country owns and the life expectancy of people who live in that country, right? Pretty tight, we agree, pretty strong, nice and positive. But it doesn't mean that owning televisions make you live longer. I mean, isn't that stupid? If you own lots of TVs as a country, you're going to live longer. Now, if that was the case, if America's wanting to help countries who have a low life expectancy, we wouldn't be sending them medicine or doctors or food. Wouldn't we just send them televisions? Do you see how stupid that is? So the number of TVs that you own does not make you live longer, right? The correlation that you're seeing between these two variables is not a causation factor. What's the real cause of this data? Why does it look so good and linear? What is the average number? Here's a clue. What is the average number of TVs that a country has? Also telling me about that country.
The average income, maybe, because they can afford more TVs.
So isn't this really a measure of the wealth of a country? Countries that have lots of TVs are wealthy, typically, right? Countries where they don't even have a TV, or half the houses don't have a TV, right? The ones way down here, aren't they probably going to be very poor countries, right? That's just the way of things. Now, wealth has a direct effect on life expectancy. If you come from a rich country, don't you get benefits for being rich? The people tend to have enough food to eat. They have good medical resources. They have, you know, all the benefits, good housing, right? Not a dangerous lifestyle, right? They don't live in a place where you're likely to get shot if you go out at night, right? Although if you go to Chicago, that's probably an exception, right? But in general, we tend to be safe. All of those things are featuring. So it's not that owning TVs makes you live longer. So you could have people who say, look at this data, see how good it is. This proves that that is that. Can you see that's a goldmine for politicians to lie to you? They will say whatever this happens to be is the reason that that's happening. And couldn't it well be something else that's really the cause? So be aware that just because there's a nice fit doesn't mean the X makes the Y happen. And that's a pretty big mistake. That's been made a lot of times. Off the top of my head, somebody conducts a survey and they find out that people who watch a lot of TV have a lower life expectancy than people who don't watch a lot of TV. Right, so if the average number of hours is, I see 1 hour of TV a day, 2, 3, 4, and this is the life expectancy of those people. Right. And someone comes up and says, watching TV kills you. That would be the newspaper article, right? Watching too much TV will kill you. Do you think watching TV on its own has any effect on your life directly? What might be another explanation for why people who watch a lot of TV don't live as long as people who don't watch a lot of TV?
People who watch a lot of TV have a sedentary lifestyle.
Yep. Couch potato people, would that seem reasonable? People who don't watch a lot of TV, couldn't the reason be that is that they like going out and doing sports and jogging and have a nicer lifestyle, and therefore, isn't that just a reflection of lifestyle? The more TV you watch, you're probably not a very active person the less you are. So it's lifestyle that you're measuring. Theoretically then, couldn't you get a really healthy marathon runner who still watches 4 hours of TV a day? Because the TV doesn't make you live longer or less. It's only a measure in the bigger picture. That's a cool question. Oh, one last, yes, we've got time for one last one. Here is another one of this problem. The x-axis is shoe size, and the y-axis is going to be reading age. So this is for children. And it's pretty good, and it's linear, and it's positive. And you read like a 5-year-old, you read like a 6-year-old, 7-year-old, 8-year-old. Does your shoe size make you read better or worse? Would you agree that is not the cause? So for children, the size of their feet is not the reason that they read good or bad, right? That they read at their age or they don't. What is the real connection between these two?
Actual age?
Yeah. Would you agree that a typical 5-year-old is probably going to have bigger feet than a 3-year-old, and a 7-year-old is going to have a bigger feet than a 2-year-old, and so on? As they get bigger, typically, don't their feet get bigger? So aren't you just really measuring the age of a child against the reading age? And that makes perfect sense. Would you agree a 10-year-old probably, on average, reads like a 10-year-old? It's... And, before I forget, we're finished. So while I'm getting my thoughts together, put your last name down. Your homework has now been extended to Monday, since Monday is a holiday, so I won't see you Monday. There won't be any office hour on Monday either. The
Does that
online
include the 90-minute test thing?
You beat me to it. That includes the 90-minute testing. So it's also going to be true. It will be visible at 2 p.m. today. So for the one person who might want that to be there, it's going to be there. But for the rest of you, you've got a few more days to worry, to work on it. And that is us for today. And don't listen to any politicians that tell you stuff, and be on the lookout for extrapolation, and correlation is not causation, right? Be on the lookout for those two guys, because they're the most common ways that people will lie to you.